Hi guys. We're going to give it a second, let other people join the class. How you guys doing this morning?
Good, how are you?
Good, thanks. You guys ready for the snow? Apparently we're supposed to get a lot. Okay, so while we're waiting for other folks to show up, just some administrative stuff. I am still grading. Please be patient. I've got like hundreds of papers I have to grade. The homework assignments, I think for our class, the homework has been done, being graded. The quizzes, I'm going to be grading probably sometime in the afternoon. And then, so you guys can start to see, once I have the quizzes graded, I'll post the solution set for the quizzes too. So you guys can get a feeling for like what the correct answers are and how you kind of work your way through it. And what you did right, what you did wrong, things like that. Quizzes are going to be a great place for you to test your knowledge of stuff and see how well prepared you are for the midterm exams and for the final exam, things like that. As a reminder, we have a quiz coming up this Thursday as well. It's listed on our Canvas page so you can see what chapter sections it is, but it'll be 2.5, 2.6, and 4.1. Okay, that's what it's scheduled for right now. So we'll we'll see how things go. And I'll collect those homeworks on Thursday. So with that said, before we finish up 2.6 stuff, anybody have any questions on the homework for 2.5 they want to go over? We can spend, about 7 minutes or so on the homework for 2.5. You guys have questions on that? You can put it in the chat if you want, or you can just say it out loud, either way. Is the homework graded just for completion? Yes, the homework is graded for completion. So what I do, it's okay for you to make mistakes in the homework, but that's also bad for you because then you don't know what you've done wrong, right? Before we get to the midterm exam, like a few days before the midterm, I'll post solutions for the homework. I don't want to post them right now because I think there may be other classes, other sections that are actually grading the homework for a grade, like for correctness. I'm not looking to see if you've done it correct or not, but I will write notes on there, like if I can see it that, I can tell that you've done like a method that's like wrong. I can, if it's obvious to me, I'll just say like see solution set or something like that. But I'm not grading for correctness, but I can tell like if you leave some things blank, then I'll circle those problems or I'll write those problems down now. And then you'll get like some fraction points back. Like, so if you've, some of you may have got like a 9 out of 10 or an 8 out of 10 or whatever, because you've only done 80% or 90% of the homework, like if you've left it blank, then what you can do is on Thursday, this coming Thursday, you can finish off those remaining problems, right? And then resubmit that homework and I can go back over and give you those 2 points back or 1 point back or whatever it is. So the homework you can always resubmit for those points back. Okay, but I am checking it just for completion. You should have a place where you can make a mistake, but please, when we get to the midterm exam, right, make sure you go back and check your homework against the solution set for the homeworks. Or if you're not sure if you did something correct, come to office hours and we'll go through and make sure that you have the correct answer for it. That's going to be important that you understand how to do the material. So yeah, be careful because I'm not grading it for correctness, just for completion. Okay, so if you want to know how you did it correct, then you'll have to compare it with the solution set. Okay. Any questions on 2.5? This is the improper integrals. I can pick one if nobody's got one. Let's see if I can find a good one. We've done number 10, we've done a lot. That's an inverse tangent function. Number 11 is good. You have to do integration by parts and L'Hopital's rule. There's a lot of stuff going on in that one. We can do that one. It's kind of a long solution. I'd be more inclined to actually post that solution online for question number 11. The answer for number 11 is -4, in case you're wondering. I think probably your book will tell you, because I think they give you answers for odd number problems. But if anybody has a question on that, I can post a solution for that because it's kind of long. Let me see what's a good one. Let's see, number 4 is, we can do I'll do number 4 unless anybody has any question. Nobody's got a question, everybody's shy. All right, so let's take a look at homework. So this is, let's get this in focus here. So this is homework for chapter 2.5. And I'll do question 4. And this way you can see something that's an even number problem, so you don't have the answer in the back of the book, but also it uses substitution, so you can get it. But if you can post it on, that's good too, yeah. So I'll do number 11. I'll post number 11 online because it's long. Number 11, it's a good question. It requires integration by parts. So it'll be good for you to see how do you do integration by parts with an improper integral. Sometimes we'll get, on the final exam, we'll get questions like this where we're testing multiple things, multiple techniques all at once, which is, can you remember how to do integration by parts and can you remember how to do improper integrals? So let me make a note of that. I will post, so question 11, chapter 2.5 post. Okay, so I'll make a note to myself and I'll post that later today. I'll scan that in. Okay, so let's go ahead and do question number 4. So 4 says we're going to go 1 to infinity. We've got dy 4y minus 3 to the 1/2. And okay, so the first of all, what I'm looking at is I've got, let me just check to see where if I have like multiple things going on. I know I've got this infinite bounds on my integral, so I know I'm going to have to do an improper integral, but I've got a function in the denominator. So let me check. So I've got 4y minus 3. I want this to be greater than 0. Okay, greater than 0. So I know that with a radical, sorry, with a radical, right, I can have it be equal to 0, but because it's in the denominator, I need it to be greater than 0. So I'm gonna, set this, right? So I've got 4y is greater than 3 divided by 4. So y has got to be greater than 3/4. Okay, so let's take a look. So y is greater than 3/4. So I've got, I have like a discontinuity. Like if y is equal to 3/4, then I'm going to have a divide by 0 problem, right? But look, my bounds are starting at 1, which is greater than 3/4. So I don't have to worry about not within bounds of integral. Okay, this is a check that you should do when you have like some kind of rational function, right? Because you want to make sure you don't end up with the divide by 0 problem. We're doing that quick check. We checked, we can see it's not within our bounds of integration, so we're good. So I'm only going to worry about the infinity part. Okay, so what that means is I need to convert the infinity to a limit process. I'm going to say the limit as b goes to infinity, and I'm going to go 1 to b. And I'm going to just start writing it like this, 4y minus 3 to the minus 1/2 dy. So I can start to think about what I need to do. Okay, so this is your first step, always to convert it to a limit process. This is the thing that we're going to be looking for. It's not going to be enough for you to go ahead and do the whole integral and at the end say the limit as b goes to infinity. We are going to be checking to see that you recognize that it's an improper integral and that the first step is to convert the bounds of integration to a limit. Okay, all right, so right, I'm looking at this here. So I'm going to think, looks like a substitution issue. So I'm going to say my u is equal to 4y minus 3, which means the du is equal to 4 dy. Well, I just have a 1 dy, so I'm going to divide by 4. So this is du over 4 equals dy. This is a u. Sorry, my handwriting isn't so great. All right, okay. So now I'm going to substitute that into here. So this becomes the limit as b goes to infinity, 1 to b. So I now have u to the minus 1/2. I have du over 4. This is d over 4 is really du times 1/4. So I'm going to bring the 1/4 through my integral. So I've got the limit as b goes to infinity, 1/4 times 1 to b, u to the minus 1/2 du. Now I can just do the power rule. Okay, when I go to integrate that. So let's see, you notice how I'm carrying my limit through every step that I do. Okay, that's important. Okay, so limit, and I need that limit there right up until the moment when I evaluate the limit, when I plug in infinity for b. Okay, so this is going to be 1/4. So this is u to the minus 1/2 plus 1 all over minus 1/2 plus 1. And don't worry about the balance because we're going to substitute back in. So minus 1/2 plus 1 is 1/2. This is 1/2, but 1/2 divided by 1/2 becomes multiplied by 2 over 1. So this is going to become the limit as b goes to infinity. So 2 times 1/4, right? This becomes u to the positive 1/2. And I'm going to substitute back in for u again. So this becomes 4y minus 3 to the 1/2. And I'm going to evaluate that from 1 to b. Okay, so I substituted back. Okay, so I substituted back in for u. Okay, so far so good. Now we're going to evaluate our limit, right? So I'm going to say, let's do our fundamental theorem of calculus. So the limit as b goes to infinity, 1/2, 4 times b minus 3 to the 1/2 minus 1/2, 4 times 1 minus 3 to the 1/2. Okay, this is going to be a number, right? You know, form basically 4 minus just 1, radical 1, 1/2. This is just equal to 1/2, right? Let's do this one. So this becomes 1/2, 4 times infinity minus 3 to the 1/2. I've got infinity, some number times infinity raised to the 1/2. So radical infinity is what we're looking at. This whole thing here, this goes to infinity, right? So infinity minus 1/2, this thing does not exist. Right, it's an unbounded limit. Therefore, we'll say our integral diverges. Okay. We had a discussion the other day in my other class. It's like, what does it mean to diverge, right? So if I plot out this function, 1 over radical 4 minus 3, it's going to look something like that. Okay, and I've got an asymptote right here. This is our 3/4, and then this is what we're trying to do. So we're going to go from 1 all the way up to infinity, right? This is my y, this is my x. Okay, so basically, right, I'm looking at a function like this. Okay, so what this means when we say, when I talk about the integral, I want to take the integral of, you know, some function between a and b. I'm talking about like an area under the curve, between the curve and the x-axis, right? So, but if I'm going from some number to infinity, that's a pretty big area that I'm looking at, right? So this thing's going to go way off. And if the diverges, it means that this area under the curve doesn't get close enough to some particular value for me to say that I can actually get a grasp on what that area is between the function and the x-axis. Okay, that means that this area under the curve is infinite area. Okay, so our integral is going to diverge, which means I can't get an area under that curve. Okay, that's the whole point about converting it to a limit process, because, right, our value for x is heading off to infinity. Infinity is like not a number, it's more of a concept. So I have to say, well, as we approach infinity, what's our function really doing? How's it performing? And the function isn't getting close to a particular value. It's still, you know, kind of cruising right along. So that's how you want to be thinking about it. Okay, so that was question number 4. You guys have questions about 2.5, we can talk about them in office hours. All right, 2.6, I think, does anybody have a question? I'm going to finish up the lecture examples on 2.6. I realized that we didn't finish up our lecture examples. We only got through, you know, part of it. But does anybody have any questions on the homework for 2.6 before I finish the chapter? I'm going to go back and finish the chapter. You can come to office hours and we can talk about it there. 25 and 26. Okay, let's see. You know what I'm going to do? Let's do this. I should have asked after I do this example. Let me finish the lecture examples first, and then I'll do these questions 25 and 26. Okay. So we'll come back to those problems. All right. So this is lecture examples for chapter 2.6. So remember, we did numerical techniques as our chapter section. And so what it means is we're talking about midpoint, which you probably remember from when you first started studying the Riemann sums from Calculus 1, right? Trapezoidal rule. So instead of building up rectangles, we're doing trapezoids, right? And then Simpsons rule, which uses parabolas. This probably should have been an upside down parabola. And then a right side up parabola to fit to our curve, okay? So these all have different formulas. they all require us to have a point on the graph, okay? That gives us the height of our essentially rectangle, trapezoid, or, you know, basically the vertex of our parabola. Okay, so now what we're trying to do is, this gives us a skill set, a technique for being able to find an integration, an integral value for a function that I can't integrate using substitution, integration by parts, improper, or whatever. Okay, this is like Simpsons Rule is actually how your calculator does it. It's a numerical method, which is a good lead into chapter 4. We're going to start chapter 4 today. And in chapter 4 is all about basically giving us numerical methods for being able to work through different types of functions. And we're going to talk about that as we go. So don't sweat it. All right, so our next part, so remember we were looking at, we're going to take the integral from 1 to 2 of the function 1 over x squared dx. And we're using 4 subintervals. Okay, so we're breaking this area up into 4 essentially rectangles or trapezoids or parabolas. So now I have to be able to subdivide that. I have to get like my width. I want these things to have equal width. Okay, and then I need different spots along my graph in order to be able to do that. So this x naught, x1, x2, these all correspond to, like, you know, sort of the demarcation lines on my subintervals. Okay. So now we did the Riemann sum, the midpoint Riemann sum. We did this one. Now this function here, you're thinking, why am I doing this numerical method when I can just integrate it? Totally true. We usually like to start off with an example of something that's straightforward. So I can absolutely integrate this using the power rule, which is what we just did here, okay, in part A. And we did that in order for you to see, let's compare it with the actual value of the integral, right? The whole point of this is to be able to use it on functions that don't integrate well. So like example number 2 on here, which I'm actually going to do offline and I'll scan it in for you because we won't have time to go through it. Example number 2 is one that I can't integrate using any numerical techniques. So I have to use all these different, I have to use midpoint or trapezoidal or Simpson. Simpsons would be the best. Okay. So let's go ahead and finish off what we're talking about here with this. So the trapezoidal rule, let's just remember. So we're going to go the integral from 1 to 2, 1 over x squared dx is approximately equal to, I'm going to write down what my trapezoidal rule is. Delta x divided by 2 times, this is my base, right? The base delta x times 1/2. Now this comes from the formula for the area of a trapezoid. Okay, so this is f of x naught plus 2 f of x1 plus 2 f of x2 plus 2 f of x3 plus f of x4. Make sure you're aware the rules for how we denote this. So trapezoidal has, the coefficients are 1 and 1 on the outside, and then 2's all throughout the inside. Okay, so my multiply, let's plug this in. So this is going to be equal to, our delta x is equal to 1/4. Okay, so this is 1/4 times 1/2, that's that divided by 2. F of x naught, so let's remember our x naught, we did all these, we calculated these out first, we prefetched them. Okay, it's always helpful to get all those numbers ahead of time. Okay, so I'm going to start plugging those in. F of x1, so this is 1 plus 2 f of x2, I'm sorry, f of x naught, f of x1 5/4 plus 2 f of 6/4 plus 2 f of 7/4 plus f of 2. Now I'm going to plug these in. This says f of, so this goes into my function. This is my f of x right here. Right, so 1 over x squared is my function. So this is equal to 1/8 times, everywhere I see an x on my function, 1 over x squared, I plug in this value here. So I'm going to go 1 over 1 squared. You don't have to square the 1. I'm just showing you like that I'm plugging it into the function. Plus 2 times 1 over 5/4 squared plus 2, 1 over 6/4 squared, that's a 6, plus 2, whoops, sorry, 1 over 7/4 squared plus 1 over 2 squared. Okay, and now do this out on your calculator. Be careful, watch out that you're summing them all up right. Sometimes when I do them all in a line like this on my calculator, I forget something, or the order of operations gets all messed up. So I've now learned to do them one at a time and then sum up all the decimals. So when I did this, I got this was approximately equal to 0.5089937,642. And again, right, we're talking about why are we using so many numbers after the decimal point, and that's because in just a minute we're going to talk about error in our approximation, and I want to be able to show you, far out. On a test, typically you only need to go out to like the 4th position here. Okay. I'm going to scroll up. All right, so Simpsons rule says, right, we're going to go our integral 1 over x squared dx is approximately equal to delta x over 3. This is our parabolas, right? So this is f of x naught plus 4, f of x1 plus 2, f of x2 plus 4, f of x3 plus f of x4. Okay, so watch out, your coefficients here have a pattern as well. The first and the last have a coefficient of 1. The second one and the second to last have a coefficient of 4, and then the interior ones alternate between 2, 4, 2, 4, 2, 4, 2, 4. Okay, so just make sure. Also, n has to be even for the Simpsons rule to be able to be used. And it is in this case because n is equal to 4. Okay, so let's go ahead and plug this in. So I'm going to go, this is 1/4 times 1/3. F of, I'm going to start plugging this in, 0 plus 4, f of 5/4 plus 2, f of 6/4 plus 4, f of 7/4 plus, oh, that's a 4, plus f of 2. Okay, so let's plug this in. So 1/4 times 1/3, 1/12. This is 1 over 1 squared plus 4 times 1 over 5/4 squared plus 2 times 1 over 6/4 squared plus 4 times 1 over 7/4 squared plus 1 over 2 squared. Watch out, don't forget this is 4 times 1 over 5/4 squared. So only the 5/4 is squared because we're plugging it into our function. Our function is 1 over x squared. I do that, I multiply by 4. I do that, multiply it by 2, multiply it by 4, but it's only the interior numbers, okay? So do it all out, multiply it out, and I get 0.5004176115. Okay, so of all of these, right, this one, is closest to 0.5. Remember, we did it on, we just did it with the power rule, and we got that. Okay. Give you guys a minute to finish writing that, and then we'll turn the page and talk about error. Error is important discussion when we talk about approximation, because error always is, whenever we approximate something, we've got some kind of error that we're accumulating, right? You think about, you do this all the time when you round up a number, you get a decimal, and I'm going to round this up to, 4.2 instead of 4.17. And so when I do that, I'm dropping all the rest of this stuff here and I'm rounding. So I have a rounding error, but I have an error that's associated with an approximation that I've made. We're going to be talking a lot about error calculations as we go. Well, I guess we're going to start talking about that today with 2.6 and with chapter 4. Because when we do approximations, we have to take into account the error that we're accumulating. Okay, so we've got the errors and the different rules. So there are different ways of calculating an error. So let's talk first about our errors and the different rules. So the first thing we're going to do is we're going to subtract our approximation answer from our actual answer, from our definite integral. Okay, so when I subtract this, basically I'm looking at, so the error of the midpoint. Now error is going to be an absolute value, because what happens with error is we say we're going to have our answer plus or minus our error. Okay, so we look at error as an absolute value number, sort of a magnitude, right, of what's happening. So I go, the error that I got in my integral is 0.5 minus, so for my midpoint, remember the answer that we got was 0.495547936480. Okay, and when I do this, I get 0.004452063. Let's do this for the other two, and then we'll talk about what's going on. Okay, so our midpoint error for our trapezoidal rule. So this is again 0.5. See, it doesn't matter if I did this one minus 0.5 because I'm taking the absolute value. I'm looking for the magnitude here. So 0.5 minus what we get for the trapezoid, 0.5 5089937647172. Subtract these out. Make sure when you're on your calculator, make sure that your like scientific notation is set out to, enough to accommodate a whole bunch of digits when you do this. 0.008993, that's a 3, 764172, and then the error for our Simpsons rule. Okay, this is 0.5 minus 0.50041761149. And then I got 0.12341761149. So this allows me to kind of quantify it better. So I've got 0.000. So I've got 3 zeros and then a number for my Simpsons. So my Simpsons has the best approximation because the error is the smallest, right? And then I go 0.004, 0.008. So surprisingly, right, the midpoint was a better approximation than my trapezoidal rule, right? I would have thought it would be the other way around, but 0.004 is smaller error than 0.008. So Simpsons usually is a better approximation in general because it's curvy. We're using parabolas, so there's more information that we're using, so it kind of fits the curve a little bit better. All right, so the simplest form of error calculation is just subtracting your actual answer from the approximation answer, right? But this sort of means I kind of have an idea about what the answer should be, right? If I'm able to do that. So the question that we really need to ask, and this gets into the whole discussion of the error, is what is a reasonable error margin? And this idea about reasonable brings up a whole discussion of things that we're going to talk about what's a reasonable error as we go along in chapter 4 and chapter 5. Because what's a reasonable error is something that, like say for example, when you're making something, someone's going to say, I want the error margins to be within 0.001. I want it to be within 0.000001. Say for example, depending on how tight you need it to be. So like for example, if you're launching a rocket from Earth and you want it to land on Mars, right? You want the error to be so small, right? Because tiny little errors are gonna be magnified over such a long distance, right? Like a tiny little error in the angle approximation is going to get magnified so that the rocket's either going to land on Mars or it's going to bypass the planet altogether. So a reasonable error for landing on Mars, the error calculation is going to be we're going to have a lot more zeros out there. We want that error to be really, 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 really tiny. So that's how we'll set reasonable. Something else, like I'm just trying to, come up with a ballpark estimate of, I don't know how many bees are in a beehive. I don't know, I'm coming up with an example. And so my reasonable error can be, 0.1. It doesn't have to even be, that small of a number. You get the idea. So what we define as reasonable is going to change depending on the nature of the condition that you're in. But it's a discussion that we have a lot when we talk about approximation, what's reasonable. So when we talk about what's a reasonable error margin. So there are equations that represent error calculations, gives us sort of like an upper bound. So if you think about upper bound on the error. Upper bound is important because I can say anything less than this is reasonable, right? Anything more than that, I think maybe that's kind of a really big error. And then if it's a really big error, then maybe I need to increase the number of subintervals, make it like make the number really large, so I have like tiny little slivers in there so that I reduce the quantities of overestimate and underestimate. So my upper bound is going to be like, let's talk about for the error on the midpoint. Right, so E for error, midpoint, I'm abbreviating things. I'm going to write down what the formula is, and I'm going to talk about what each piece is. Okay, so I'm going to have M times B minus A cubed all over 24n squared. Okay, you don't worry about memorizing these things. These are things that are going to be for you, to kind of practice this stuff. Let me fill out what these are, and then we're actually going to do some. So here's midpoint, error for the trapezoidal rule. It's going to look like MB minus A cubed all over 12n squared. And then error for Simpsons is going to look like b minus a to the 5th all over 180 n to the 4th. Okay, so let's talk about what things are, right? So our b and a are our bounds of integration. N is the number of subintervals. M is going to come from, let's write down what m is, and then we're going to fill out these answers. So m is the maximum value of the absolute value of the second derivative of x. Okay, the second derivative of x for the trapezoidal and midpoint rules. And then for Simpson's rule, we have to use the fourth derivative of x. So Simpson's has a, tighter error margin, right? So, and we're going from a to b. This is our bounds of integration, and n is our subintervals. Okay, so then basically the process that we do is we're gonna take our second derivative of x, or our fourth derivative of x, depending on what method you're doing, right? And then the second thing we're going to do is we're going to plug in a, we're going to plug in b for x, okay? And then we're going to find maximum value. Oops, maximum value. So whichever of these boundary values gives me the maximum number, right? So let's go ahead and do it. So, so my function, let's do my first derivative, right? So my function itself is equal to, so if my function is equal to 1 over x squared, which I'm going to write as x to the minus 2. So my first derivative is going to look like minus 2 x to the minus 3, right? I'm using my power rule on my derivative. My second derivative, right? I'm going to go minus 2 times minus 3. That's going to give me 6 x to the minus 4. Okay. So for trapezoidal and midpoint, what I'm going to do is I'm going to say this is going to be 6. My a is equal to 1. B is equal to 2. This came from our original problem that we just did. So 6 times 1 to the minus 4th is just equal to 6. Okay, this is our a. And now I'm going to go 6 times, oh, give me a sec. 6 times 2 to the minus 4. When I do this, I'm going to get 6 over 16. Okay, so then this is my maximum value. Okay, and that's the value that I'm going to plug in for m, right, on here. Okay, this is going to get me that. All right, equal to m. Okay, let's do our third derivative for our Simpsons rule. Third derivative, right, so 6 times minus 4 minus 24. X to the minus 5, and our fourth derivative, f to the 4th, right? So minus 5 times minus 24 is going to give me 120, x to the minus 6. So I'm going to take this and I'm going to go 120, 1 to the minus 6, that's 120. And then this is my a, or I'm going to go 120, where's my 2? 2 to the minus 6, and this is 1.875. So this here is my m for Simpsons. And this is for trapezoidal and midpoint. Right, so this is the m value that I'm going to plug into here. Okay, so I plug in 6 times 2 minus 1 cubed all over 24 times 4 squared. Right, so this becomes 6, what did I say, 2 minus 1 cubed all over 24 times 4 squared. And what did I get out of here? I got 0.0156. I did this again here, and I got 0.03125. And I did this for Simpsons. So for m, I chose 120. So I chose 120 for m, right? And this is going to be 4 to the 4th. So this is 120, 2 minus 1 to the 5th, 180 times 4 to the 4th. And for this one, I got 0.00260. Okay, these are upper bounds on the error. And that helps us be able to determine, right? So if my upper bound, I'm saying anything less than 0.01 is a pretty good estimate, right? So 0.004 is less than 0.01. So 0.004 satisfies our question of, is this a reasonable upper bound? Is this a reasonable error margin? 0.03, that's, pretty loose as well, right? 0.008 is less than that. 0.002, we have 0.0004, right? So see how this error 0.002, like this one, wouldn't have been satisfied, but it's for midpoint, but this is the error margin for Simpsons. Okay, so even still with the error margin that we found for Simpsons for n equals 4, this was pretty good. So what would I do if I got an error margin that say this was outside of this one, outside of my reasonable estimate? Well, then what I'd have to do is I would probably need to increase the number of subintervals that I was working with, because it's the number of subintervals, right? If you take a look, right, this is a pretty wide, I've got 4 subintervals on here, but if I made them if I did tiny subintervals, so say I had 16 subintervals, right? Or 32 subintervals, or even 100. I think our calculator probably uses hundreds or thousand, subintervals when it does these calculations, so that we really minimize this under and overestimate point, right? And when we do the trapezoid, all this stuff right here that's underneath the curve or over, right? We're gonna avoid that. Okay, so that's our reasonable error. But we don't typically think about on the midterm exam when we do these calculations, we don't typically ask about error for approximation on here. For that, we just we'll give you a function and we'll say do midpoint or trapezoidal or Simpsons, and then you'll have to come up with an answer for it. And if you use the wrong n, or if you use the wrong method, then the answer will be slightly different. Okay, so keep that in mind. So this is reasonable. Like I said, the second example, which is the integral of e to the minus x squared, I'm going to do that offline and I'll scan that in and give that to you, because it's it's got a lot going on there, and we need to move on to chapter 4. Okay, so I'll let you guys finish writing that, and then I will answer. It looks like why don't I just choose one of those questions, and then if you have a question on one of those, then you can come to office hours and we can talk about it. Let's see. Okay. Yes, this is a pain. This one takes a long time. Okay. Right, yes.
Professor, can you go down a little bit?
Yeah, you
The
bet.
camera.
How's that?
Yeah, perfect. Thank you.
You're welcome. So 25 and 26 are really tedious because you have to do n equals 10. What I'm going to do is I'll set it up. Maybe I'll do, let's see, I can do 26 doesn't have a solution for it because it's an even number. But why don't I do 26 so I can show you what that looks like. You guys all set with this one here? All right, so I'll do that and I'll scan that in later. So let's take a look. All right, so this is chapter 2.6, question 26. And 25 and 26 are actually related. So 25 says we're going to use, where they say, use the natural log of x equals the integral from 1 to x dt over t. And they want to use, so 25 says use the trapezoidal rule with n equals 10 to approximate the natural log of 2. Okay, so what do we have to do? So that means basically, let's set this up. I'll start to set this up. This is like part of chapter question 25 helps you set it up. So I'll kind of do a little bit of both. So what I need to do is we're going to do the to approximate ln of 2. Well, this gives me a clue. I'm going to say my x equals 2, right? Because that's they're telling us that it's kind of a trick question where they aren't telling us what the bounds of integration are directly, but we kind of have to intuit it. So what this is I'm going to say from 1 to 2, I'm going to go dx over x, right? And I'm going to do n equals 10. And just for reference, natural log of 2, 0.69314. So I'm going to keep that in the back of my mind to think, is my answer close to that? Because I can get this off of my calculator, right? So let's go ahead and set this up, right? So if I were to, and you would get this like just taking the integral where I go just to do this directly. So I get the natural log of x from 1 to 2, and then I would evaluate that, and I would get this number here. Okay. Or you can plug it into your calculator. All right, so let's do, so 25 says trapezoidal rule, 26 says Simpsons rule, but I'll do Simpsons rule because you don't have 26, you don't have a solution in your book for that one. But first we have to prefetch certain things. So I have to calculate what my delta x is, b minus a all over n. So I'm going to go 2 minus 1 all over 10. So my delta x is 1/10. So it's a pretty nice narrow sliver. That means that I have to calculate my x naught. I'm going to start at 1. Then my x1 is going to be 1 plus 1/10, right? Because I had to go from that where I'm starting from plus my delta, right? It's the same delta either way. And then x2 equals, this is going to be basically x1 plus 1/10, and so on and so forth, all the way down to x sub 10, where I'm going to be ending off at 2. Let's do x sub 9, which is going to be x sub 8 plus 1/10. Okay, so basically, I'm just going to write this as, I'll write this as 1 plus 2/10, you know, and then 1 plus 3/10, 1 plus 4/10, 1 plus 5/10, and then this becomes 1 plus 9/10, right? And then this becomes 1 plus 10/10, which is equal to 2. Okay, so I would plug those into trapezoidal rule for 25, question number 25, and then Simpsons rule for 26. So question 25. Your trapezoidal rule formula, question 26, Simpsons. So let's go ahead and do the Simpsons one out. So this one's going to be, remember our Simpsons rule says I'm going to go 1 to 2, 1 over x dx is going to be approximately equal to delta x over 3 times f of x naught plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus 2 f of x4 plus 4 f of x5 plus 2, oops, sorry, there's an f of x6 plus 4 f of x7 plus 2 f of x8 plus 4 f of x9 plus f of x10. Okay, remember 1, 1, 4, 4, and then 2, 4, 2, 4, 2, 4, 2, 4 along the way. Okay, so we're going to plug this in. So this is going to be 1 over 10. That's our delta x times 1 over 3, right? So then I'm going to plug this into my function. This is 1 over x, right? So this becomes 1 over 1, right? I'm plugging in these values, plus 4 all over 1 plus 1/10. I'm being lazy and not actually writing it out. Plus 2 all over 1 plus 2/10, plus 4, 1 plus 3/10, plus 2, 1 plus 4/10, plus 4, 1 plus 5/10, plus 2, 1 plus 6/10, plus 4, 1 plus 7/10. Sorry, you can't see that. Plus 2, 1 plus 8/10, plus 4, 1 plus 9/10, plus 1 all over 1 plus 1. This is my last one. That's my 2. All right. And then I just did it out on my calculator, right? I already plugged this into my function, right? My function is f of x is 1 over x. So then I got, this was approximately equal to 0.69315. Okay, so this is using Simpsons. It's just really tedious. My n equals 10. Why did they give me an n equals 10? I have to do all the work out. It's hard. Actually, it's not hard. It's just, boy, it takes a lot of time. And you're going to find that to be true when you do these, that give yourself plenty of time because they just take a lot of time to do. Okay, give you guys a chance to finish writing that. And then we're going to move on to chapter 4. Okay. All right, so let's talk chapter 4.1. Okay, so chapter 4.1 is called Approximating Polynomials. All right, so let's take a step back. Chapter 4 is all about actually using polynomials to approximate other functions that are not polynomials. So let me write a subtitle: Approximating Polynomials with Polynomials. Oops, Polynomials. Okay, this is kind of like, I'm going to subtitle this as an introduction to approximating complex functions, things like e to the x, sine of x, cosine, trig, exponentials, logs, things like that, rational functions, to approximating complex functions with simpler polynomials. Okay. Chapter 4.1 actually gets a little confusing because we're approximating simple polynomials with another polynomial. And you kind of ask yourself that question, well, why would I do that? Because the polynomials are already polynomials, they're easy to work with. And the whole point about 4.1 is to use something that's simple, like a polynomial, and use another polynomial to approximate it, just to give you the terminology and the methods. Okay, and then, so don't overthink 4.1. Okay, 4.1 is just like kind of overly simple. It's an introduction. Okay, so I'm going to use a lot of vocabulary, introduce some concepts, right? And then 4.2 and beyond, we're going to take it and we're going to ramp up into approximating complex functions with more simple polynomials. So 4.1 is using a polynomial to talk about another polynomial, just to give you the methodology for it. Okay, so let's come up with some terminology. So my polynomial, I'll call P of x, polynomial of, it's a function of x. It's an algebraic expression, right? And then, so our polynomial function is the function that's defined by our algebraic expression. Okay, all right, so let's talk our general polynomial. Looks something like this. I know it seems you guys probably already know this stuff. We just need a common terminology. So I've got a constant term, c sub 0, right? And that's times like x to the 0, right? So c sub 0 is just my constant term plus c1 x to the 1. I don't usually write x to the 1, but I'm putting it there so you can see it has the same subscript. Plus c2 x squared plus c3 x cubed plus so on and so forth, as many terms as I want. Right, and we're going to see as we go along in chapter 4 and chapter 5 that I can actually have an infinite number of terms in my polynomial. We obviously don't write them out, and that's the whole point of our approximation, but we can define it to as many as we want. Now I can write this in summation form, right? I've got my summation terminology here, where I can say k equals 0, and I'm going to go all the way up to some number, right? However far I want to go up to, I'll call it, I don't know, whatever, d for degree, right? So I've got c sub k, x to the k, where d is the degree. When we wrote n before, I mean, all these numbers are like dummy variables, right? So k and d are and those are all dummy variables, okay? So we can say degree of the polynomial. Degree represents our highest degree term, right? Or it's a cubic, it's a quartic, it's a quadratic. And then c sub d does not equal to 0. We are going to define x sub 0 equals to 1, just to remind us. And we're going to say this is true even when x is equal to 0. So we're basically going to say, we're basically going to define 0 to the 0 equals 1, okay? Even though we know that 0 to the 0 is undefined. Okay, so we're defining this right here, okay? Just so we can come up with the general form of our polynomial. So let's talk about, let me write down something and I'll talk about what it means. So really important point, when x is close to 0. So when my x value is close to 0. So when x being close to 0, that means x is equal to 0.000001, say for example, right? So when x is close to 0, the higher powers of x are even closer to 0. Okay, what does that mean? That means like if x is close to 0, so it's like 0.0001, right? If x is close to 0, then x squared is closer to 0. So I've got 0.001 squared, right? 0.001 squared is going to be even closer to 0 than x was, right? Because I've squared this really small number. Okay, so our goal here, also I want to point out that our goal is to approximate, right? I want to approximate. I'm going to try to get as close to 0 as I can. I'm going to try to approximate. So this polynomial that we're using to represent our complex function ultimately is going to be an approximation of that complex function. Okay. All right. So I've got my lecture examples for 4.1. Okay, I'm going to pull that out and take a look. So I've got this polynomial here, 4 minus 2x plus 5x squared plus 9x to the 5th. Now let's take a step back first and unpack this. So this right here, we're accustomed to thinking of polynomials as being written from the highest degree term on down. We're going to reverse that now and start off with our lowest degree term and work our way up. And why do I do that is because I'm going to be ultimately representing polynomials with an infinite number of terms. I don't want to start with an infinite number first and then work my way down. I'm going to start with the smallest number first and work my way up. Okay, so I've got my smallest degree term and I work my way up. So what's the degree? What are the partial sums? What are the partial sums when x is equal to 0.1, when x is equal to 0.01? So I'm going to be talking about vocabulary and doing stuff through this example. Okay. All right, so let's take a look. So let's let me just first write out. So when x is close to 0, x squared and x to the 5th are really small, right? You can imagine, right? Remember what we just did. Like if I plug in 0.001 and I square 0.001 to the 5th is even smaller. Those terms are contributing less in terms of getting me closer to some value because they're such small numbers, right? So these numbers are really, really small, and therefore they tend to drop out in terms of their contribution to the final answer. If this doesn't make sense, don't sweat it, roll with it. Okay, we're going to do the whole thing and then you'll start to see what I'm talking about here. Okay, so let's first go back to this question. What's the degree? So the degree, we're going to talk about, I'm going to write it like this, p to the n of x. Okay, this is like my degree term. So I'm going to call this, this is the sum of all the terms up to x to the nth term. That's a t. Okay, we call these partial sums. We call it like the first order partial sum, second order partial sum. I don't know if you've heard that term, but let's do it out. So I look at what I have. I say my 0th order partial sum. I'm going to go all of the terms up to and including the highest degree term of 0. That means this is like 4, and I'm going to write this in a different color. 4 times x to the 0. Remember, x to the 0 is equal to 1. So see how that 0 degree term matches that 0 degree term there too. My first order is all of the degree terms summed up until x has the highest degree term of 1. So I've got my 0th term minus 2x, and I'll write the 1 in a different color. So that 1 matches this one here. So the highest degree term is equal to, this says I want the first order, so my highest degree term is a 1. Okay, let's do it for the other one. So p sub 2. So I'm going to take all of them. So 4 minus 2x to the 1 plus 5x squared. I'll circle these so you can see they're the same. This one and this one, the highest degree term. my third order partial sum. I don't have a cubic in here, but what I'm going to do is this, watch. So 4 minus 2x plus 5x squared plus 0 times x cubed, right? So what I've done is my highest degree term is the cubic, but the coefficient is a 0. So my third order partial sum is equal to my second order partial sum because my coefficient of x cubed is 0. Let's do the same thing for the fourth order. So 4 minus 2x plus 5x cubed plus 0, oops, sorry, squared, plus 0x cubed plus 0x to the fourth, right? So actually my fourth order is equal to my third order, which is equal to my second order because the coefficients of x cubed and x to the fourth are 0. And it just happens. That's just the nature of this polynomial that we're working with. We're using this as an illustrative example. All right, to the fifth. So I'm going to go 4 minus 2x plus 5x squared plus, now I'm writing out the zeros here so you can see them, but in reality, I can just go like this, 9x to the fifth. Right, so this is my highest degree term. This is my highest degree term. So this is my fifth order partial sum. I'll do my sixth order partial sum just so you can see, you can imagine 9x to the fifth plus 0x to the sixth, right? So my sixth order partial sum, seventh order, eighth order, ninth order, 10th, whatever, they're all going to be equal to my fifth order partial sum because that's my highest degree term on the polynomial that we were given. Okay, and then I'll write, etc. Okay. Seventh order, eighth order, ninth order, so on a 100th order, it's going to be the same thing as my fifth order. Okay. All right, so let's talk about the next one, next part, which says when x is equal to 0.1. What does it look like? Let me talk about what's going on. So I'm going to look at my partial sums and I'm going to plug in everywhere I see an x, I'm going to plug in 0.1, sorry. So my 0th order of x is equal to 4, right? I don't have an x I can plug into. My first order partial sum is equal to 4 minus 2 times 0.1, right? See, I'm plugging in 0.1 into my x, and that's equal to 3.8. My second order is equal to 4 minus 2 times 0.1 minus, I go up to my second order, right? This is 5, oops, that's a plus 5, 0.1 squared. And this is equal to 3.85. Okay, well, you're probably wondering, why am I going through and doing all this stuff? We're starting to learn why we're doing this. Essentially, when we do these polynomial approximations, we're looking for values of x that are close to a particular value. And we're going to see why that is later as we work through these problems. My third, or actually I don't have to worry about my third, I'm going to do the fifth order. So I'm going to go 4 minus 2 times 0.1 plus 5, 0.1 squared plus 9, 0.1 to the fifth. And that's going to equal to 3. Let's see what I get. I think that was 85009. Can't read my writing. Is it 8 or 7? I'll do this out. 4 minus 2 times, oops, times 0.1 plus 5 times 0.1 squared plus 9 times 0.1 to the 85. Okay, good. Okay. Let's make x even closer. We're going to see what happens. I'll roll through this again too. And now technically I could put in p prime, p to the first degree of 0.01. We're plugging that in. That's what we're actually doing. Actually, I'm going to skip the first order. We're going to do 2, 0, 1 plus 5 times 0.01 squared. And this one's equal to 3.9805. Oops, sorry, there should be an extra 0 in there. Squared plus 9. Okay. So you can see that adding that 0.01 to the 5th, all it did was tack on this extra set of zeros and a 9. So this contribution was very small, which is what we were talking about when we said as x gets closer to 0, right? These higher degree terms are contributing less to an actual answer. Okay. You'll have problems like this in your homework. Okay.
Would the degree for this polynomial just be the 5th degree?
This is a 5th degree, yeah, 5th order polynomial. If we ask you for, I want to look at the second partial sum, then I'm just looking at here, which is something that we might ask. We might say, you know, given the first order partial sum or the third order partial sum or 5th order partial sum, what is that? What's the answer when x gets close to 0, when x is equal to 0.01? So those are, we're starting to use the terminology called the partial sum. And that partial sum becomes important because when we have a polynomial that has an infinite number of terms, we're going to represent that. Obviously, we can't say I'm going to use a whole all infinity, right, number of terms. I'm going to say I've got like a 10th order, 100th order partial sum or whatever to represent some function. Okay, so we're trying to learn this terminology, and then y, right, as I'm getting close to values of 0. Okay, and I'm focusing on 0 in this particular case. We're going to focus on other numbers. And why am I focusing on 0 here and the number 2 elsewhere? Say, for example, it's going to depend on the function that you're working on and why you're doing that. Well, we're going to talk all about that as we go. Okay. So this is example 2 is a lot like you have a homework problem that's almost identical to this. So we've got the same polynomial. If x is close to 0, what power of x best approximates p of x minus 4 plus 2x over 5? Now, don't overthink it. Really, what we're doing is, let me rewrite this. So p of x equals 4 minus 2x plus 5x squared plus 9x to the 5th. Okay, so I want to be able to, this is like a number right here. So what I'm going to do is I'm going to subtract 4 from both sides. I'm going to get p of x minus 4 equals, right? This is going to be minus 2x plus 5x squared plus 9x to the 5th, right? So now what I want to do is I want to be able to add 2x, right? Because look at what I have here. I'm going to add 2x. So I'm going to get p of x minus 4 plus 2x equals 5x squared plus 9x to the 5th. Well, this is divide by 5, so I'm going to divide both sides by 5. This is going to look like p of x minus 4 plus 2x divided by 5 equals x squared plus, this is technically 9/5 x to the 5th, right? So the question is, what, as x gets close to 0, what power of x best approximates this thing here? So I've got it. Now, remember what we just said, that this term is going to contribute more to the answer than this term as x goes to 0, right? So 0.001 raised to the 5th is going to be a really small number. It's going to be much smaller than 0.001 squared, okay? So this one is going to be the better approximation. So x squared best approximates p of x minus 4 plus 2x divided by 5, because it contributes more to the answer than x to the 5th does as x approaches 0. Okay, we're just trying to get you to think about things differently. Okay, we're trying to open up your mind about what this means. Okay. Okay. Let me just talk really quick about error and approximation. We have a few more minutes to talk about error and approximation, and how we do our error calculations. Every time, like I said before, anytime we do an error, anytime we do an approximation, the difference between our approximation and our actual or expected answer becomes something we need to measure. Okay, so I'm going to want to talk about, let's see, first I'll talk about first a definition right? So there's a thing called the remainder, the nth remainder. So when we have our partial sum, right? Say, for example, let me go back to, I have my partial sum. My second order partial sum is 4 minus 2x plus 5x squared. But what did I leave off? From my original polynomial, I had 9x to the fifth. So 9x to the fifth, the bit that I left off becomes the remainder, okay? The remainder is important because what I'm having to leave behind helps me calculate the error in approximation. So let's talk about this. We're gonna call q of x is gonna be our polynomial. And I know I'm using a different variable here, and that's just to kind of get you to think about, so p, we don't have a lock on using the letter p for polynomials. Q raised to the n, this just tells us we have an nth partial sum. Okay, so my polynomial could be 10th degree. I'm only looking at my second order partial sum is going to be all things just up into x squared terms. Okay, and I'm going to discard all the rest of the terms. Okay, but the things that I'm discarding become part of my remainder. So r for remainder, n of x becomes what I've left over. So this is my original polynomial minus the partial sum. Okay, this is my remainder. Okay, so this is the bit that we're leaving behind when we use our nth order partial sum. Our n of x is the part of polynomial that we leave behind when we use an nth order partial sum. Let me finish up this quick definition of the error, and then we'll end, and then we'll continue this on Wednesday. Okay, so our definition of our error in approximation. Okay, so I'm going to approximate some polynomial with a partial sum. So I'm approximating q of x by some partial sum. Approximating q of x by a partial sum, qn of x. Okay, just like we did before, we said I'm going to take the third order or second order partial sum, and I left stuff behind. Okay, so what this means is I'll say my error, E for error, is the magnitude of the remainder. Okay, so we would say that our partial sum approximates our polynomial, right, by plus or minus our error. Right, I've got my approximation, you know, my polynomial plus or minus this error is the approximation that I'm doing. Okay, and I can write it out like this. We'll write it out in math. Minus my error is less than my polynomial, which is less than my approximation plus my error. All I did was say, you know, right, I took this, I said q of x is going to approximate. So I've got this part in the middle, and then I subtract it and I add it. So all I did was create an inequality by rewriting this part right here. Okay. There's a lot to take in. 4.1, don't overthink it. We're just using polynomials as a basis for approximating other things. Take a stab at the homework tonight for 4.1. Probably you can do like parts of it where they say the parts that look like, excuse me, there are a lot of questions that look like this question here, which is why I did that one first, and then some questions that look like this. So you can do those problems, okay? Take a stab at those tonight, and then we'll talk about them on Wednesday. And if we split up chapter 4.1 on the quiz, maybe we'll just do the first part of 4.1 for our quiz, okay? All right, you guys, hey, have a great day. Be careful, I hear it's gonna snow, so be careful if you go out into the snow. And I'll see you guys again on Wednesday. Bye.
Thank you.
Thank you.
Thank you.
Thank
Bye.
you.
Thank you.
Bye, take it easy.